Hello, this is John Golden, and we're here to solve a couple problems. Today's problems that we're going to think about are trigonometry problems. Okay, so our first problem here is kind of an application of trigonometry. We want to read the problem carefully. So Avi is trying to draw a map of his most recent bike ride. He chose to place Market Street on the x-axis, Broad Street on the y-axis. I'm going to check. Oh, okay. So they're just matching the picture here. He rode 60 meters at an angle of 60 degrees relative to Market Street. Okay, so this is one of those goofy math problems. 60 meters, that's about 60 yards. That's not very far to ride on a bike. Then rode 100 meters at an angle of 45 degrees. And finally rode 35 meters directly north on Broad Street. Okay, so just looking, if I had to be quick, the picture looks kind of roughly proportional. The 100 is longer than the 60. The 35 is about half of the 60. So I think the picture is pretty accurate. If not, I could draw my own accurate picture. The 100 would be down around here, right? So this distance here, that 115 looks pretty close. 35, no way. But then we do have to add the 35 to it. So 35 plus 100 plus a little bit. So this looks like that's out also. So maybe it's this. This looks very trigonometric. Let's see, square root of 2 is about 1.5, so 75, 1.5, 45, 110, 115. This is around the 115. I'm guessing that's too small. And this one, to me, it also looks promising because this is going to be some kind of trigonometric sort of thing. This is going to be some kind of trigonometric sort of thing, and then plus that 35. My money's on E for this problem. Okay. All right. So to figure it out exactly, what we want to know is this distance. How many meters north of Market Street? Okay, so if we know this distance, 35, this distance, kind of the vertical, the north part of the 100 meters, and then this distance. Okay, so if this is the angle I know, the side I want to know is opposite. So even as well as I know trigonometry, I still tend to think about this, comes to mind to remember. All right, so I'm talking about sine here. So this is telling us the sine of 60 is the opposite, which is that distance we want to know. Call it whatever you want. Over the hypotenuse, which is the 60. Okay. Sine of 60, you can do it on your calculator, but be careful, the answers have the square roots in. So you can do a lot of the numerical kind of back and forth, or you can try to remember. For me, I think about the unit circle. The sine is if you've got some angle, right? The sine is the opposite, so the sine is the y-coordinate. So sine of 0 is 0, sine of 90 degrees is 1, and then it goes up 30, 45, 60. So this is the one that's square root of 3 over 2. I don't know if you've never ever noticed this, but sine and cosine go in this pattern. But 1 is square root of 4 over 2, and 1/2 is square root of 1 over 2. So it's really square root of 1, square root of 2, square root of 3, square root of 4. So 30, 0, 30, 45, 60, 90. Okay, anyhow, long story short, too late. We're saying this is the square root of 3 over 2. So that means multiply both sides by 60 to get because what we want to find is how long that distance was. And we get square root of 3. 60 divided by 2 is 30. Interesting. The plot thickens. All right, so I'll double check, make sure. Oh, what did I say? Square root of 3 times 30. Oh, no, that's this one right here. Okay, so now we want to know this distance. I'm guessing it's going to work out the same, so that 50 times the square root of 2, because 45 degrees is going to be the square root of 2. But let's set it up just to be sure. So the sine of 45 degrees is going to be this distance that we want to know divided by the hypotenuse, which is 100 this time. So we've got this triangle 100. If it helps you, it might be worthwhile just kind of redrawing that triangle by itself. So this is 100, this is some distance we want to know, and then this angle is 45 degrees. So this, we know sine of 45 degrees. That's the one that's the same for sine and cosine, because it's halfway between. So y is going to be equal to 100 square root of 2 divided by 2. Y is this 50 square root of 2. So that's the second piece. And then the third piece is up here. One of the things to watch for distractors, right? They've got this to catch those people who are like, oh, there are my two numbers. Reading the problem carefully, though, reminds us of this, which in this diagram is really tricky because the first time I looked at the picture, I did not notice that 35 there. But this one is definitely E. Okay, so let's see what else we've got. So we've got another trig problem here. This one involves kind of basic definitions of functions. So if you can remember, these will typically be pretty easy to work out. And in this one, it's nice they gave you these three values. So it's a little confusing, the names. The names are quite old historically. So cotangent, 1 over tangent, that's kind of easy to associate. But how do you remember secant and cosine, and cosecant and sine? So I've had some students who say that just remember there's never more than one co. Only one co per these pairs. I don't know if that'll help you remember or not. Okay, so g of x they're saying is cosecant times tangent. So one of the ways to do these identities is to break everything down to sines, cosines, and tangents, or sines and cosines, excuse me. So cosecant is 1 over sine. Tangent, oh, it's not in here. What is tangent? Oh, so well, remember, just like in the last problem, so ca, those are opposite hypotenuse, adjacent hypotenuse. Toa, opposite over adjacent, that's the sine over the cosine. So okay, so sine x divided by sine x, that's just 1. 1 over cosine, not an option here. So we've got to remember, they even gave it to us here. The 1 over cosine, that's the secant. So again, part E. So what we're learning is always take E. Just kidding. All right, so the secant, kind of remembering these relationships. What else could you notice about this problem? An identity, right? It was really what we're doing here is an identity, because this cosecant times tangent is always equal to secant. So when we get these equations where we're saying that this is always equal to that, Sometimes you'll see that referred to as trigonometric identity. All right. So one of the things, if you want to go in depth, most of the trigonometry on these tests is not super in depth. But if you want to understand at some point trigonometry more deeply, this is a picture that I give to students in my classes. So it looks at everything geometrically. So if you're a visual person, this might help you think about that. So up here, right? It's always about similar triangles. So all these relationships we were just talking about come from this picture. So remember that this distance is 1, this distance is 1. We're thinking about this in the unit circle. So in all these triangles, like when we say sine of the angle over cosine of the angle, if we check another triangle, we can see something else it's equal to. Corresponding sides, the sine is like the tangent, and then the cosine is like the 1. Oh, so tangent is sine over cosine. What if we do cotangent, right? This would be a weird one. So we can say cotangent's in a triangle with cosecant. So cotangent over cosecant, that's like this side, cosine over the long side is the hypotenuse. So cosine over the hypotenuse in this one, that's that 1 to the unit circle again. Okay, so this image right here has all the trigonometric relationships in it. And it makes a little more sense. Why do we call the tangent? Is because it's tangent to the circle. The cosine is the co of the sine because it's in the triangle with the sine. So it's the co-value for the sine. So those are some of the basic trigonometric relationships. I hope this was helpful. As always, remember you can submit problems to me. I'll make the videos. If you just have a quick question, I can email you back. Remember, I have online office hours Monday nights. The link is on the course page, the syllabus, and on Piazza. So thanks very much. I hope this helped.